Swayam Prabha. Digital India. Educated India.
So, today we will begin a new topic on stocks and flows. The stocks and flows forms the central concept for this entire system dynamics methodology, and we will be spending most of our time this course worrying about the stocks and flows and trying to model them and using that construct to understand and model and simulate various systems. But before that, I would like to give a brief history of system dynamics methodology, which some of you might find fascinating. This is one of those rare approaches that has a definitive founder or a creator who had developed this methodology. So, the system dynamics methodology was developed by Professor J.W. Forrester from MIT in the mid 1950s. The interesting was Professor Forrester was a electrical engineer by training, and he was even participated and headed the project on the whirlwind project, as it is called, in the 1940s, where he had helped develop the kind of a storage device which is a precursor to today's RAM. So, with that solid foundation, in the mid 1950s, when the Sloan School of Management was started, he was invited to be on board, and being a true electrical engineer, he told, like, I don't know nothing about management, why am I being part of it? They just said, okay, you just come and see what you can do. So, being an electrical engineer, he had a good sound background in the areas of control theory. So, he thought, okay, let's see whether we can apply some of those concepts into management. So, he spent a year or two looking at various industrial processes and trying to map it in terms of a kind of a control theory kind of approach, where we look at the state of the system and see what kind of things flow in and out, and the result was this fascinating field of system dynamics. So, what he did was to look at industrial systems, where he identified various players within a supply chain. So, even at that time, people were not even common in using the term supply chain, kind of initiated saying, okay, let us assume there are some, he went and studied some of it, and okay, there are these factories, there are these warehouses, and there are these retailers, and warehouses orders material to the factory produces them, and after some time the material reaches the warehouse, and even before ordering there are various sorts of delays that can occur, and he systematically wrote them out as a set of equations, time difference equations or differential equations as we see it, and the end result was this interesting book on industrial dynamics, which he came out in 1961. So, where he actually identified the business structures, looked at the sales, inventory and order policy in a very systematic manner, and looked at the business, the expanding effects of supply chain due to fluctuating retailer demand. And this book, now it is known as the bullwhip effect. Some of you might have heard of the bullwhip effect. It has its origins right here in 1950s work of Forrester. At that time, he didn't use the term bullwhip effect, he just pointed out the fluctuations, and very interesting and new to that period in time, this book is full of illustrations. It has full of computer generated graphics to show how, if an inventory changes, what happens to dynamics upstream within the warehouse, retailers, warehouse, distributors, as well as the factory. But to do that simulation, remember we were 1950s, and that's when computer was getting set up. Each computer was probably as big as this room. There is probably handful of computers in the entire United States, and predominantly was used in the Manhattan Project and stuff. So, MIT had one. So, he had approached the computer department, and I told, hey, I have set up these equations, but I can't solve them. They are getting highly nonlinear. So, can we actually try and simulate them? So, the computer department took it up as a challenge and built this simple, standing for simulation of industrial management problems using lot of equations. That is what simple stands for. That was the very first attempt to move away from coding, in the coding sense, to bring it into a symbolic language, because what we have on the on the top side is just a set of differential equations, and using that symbolic structure we want to simulate the system. So, we do not, so that was the very first attempt to actually move away from coding into a use of a symbolic structure, so that that can be used by others who are non-coders. So, its foundation went way back in 1950s, almost the very first development of and use of computers, and this is probably one of the very early use of computer for other than military purposes. That has later developed, later meaning within next decade itself led to the development of what is called as dynamo, standing for dynamic models with a little more powerful interface, which does based on symbolic input, it could use to simulate differential equations and dynamic systems. That's what dynamic model means, and this spurred the development and use of computers by non-programmers. That had a very interesting origins. So it is not that the programming came first and then we went this. In fact, effort to develop and use computer models for non-programmers started way earlier than you might have known. So, when this industrial dynamics came, that was very new. We are looking at unit management or industrial systems. Nobody has looked at the system as a set of equations that can be modeled. That was kind of well received, but soon the potential for this approach in other domains became apparent in the mid entire 60s, when Forrester had encounters with other colleagues in various departments as well as in the administration. The result was in 69 he helped work on urban dynamics, where he looked at more problem of cities and urban development, where he was able to use the same system dynamics methodology to actually map and identify various variables as stocks and flows, with the underlying structure as being a differential equation concepts. And then in 71 he helped develop this world dynamics, a model of how the world population evolves, the energy needs, environment, etc. way back in 1971. Now, all these three came out as nice big fat books. So, what it did, and then Forrester devoted rest of his life to the expansion, the education, as well as the use of system dynamics methodology for various societal problems, as well as looking at complex issues and how to abstract them. So, all these work helped initiate this dialogue on whether how feasible the modeling of societal problem is. Still, of course, it's an ongoing debate. You may find people are either really into system dynamics and take it, or they just dismiss it out front, saying no, this is still giving us a very still model. There are still more complexities which you can't capture it. So, it's still ongoing debate. But it all stems from Forrester's early argument, where he is told that use of computerized system models, which he believed in, use of computerized system models to inform social policy is far superior to simple debate, both in generating insight into the root causes of the problem and in understanding the likely effects of proposed solutions. Way back in 1971, which hopefully some of us will share. The idea here being, when we engage in come up with, when we are looking at a social or a more complex socio-economic kind of problem, we need various viewpoints. We can't just sit in a room and just ideate on what will work. So, when we start to engage in dialogue, it eventually leads into, moves away from dialogue to discussion to heated debates on various forefronts. So, what this can help bring to the table is, as and when various viewpoints are presented, we can try to map it out in a kind of nice causal kind of diagram, and identifying stocks and flows, and then trying to understand how the dynamics evolve over time. Yeah, so that's kind of nice history of how system dynamics has evolved. When it started off directly by identifying the stocks and flows that we are going to see, and only later people told that jumping to stock and flow itself is quite difficult. Let us first develop what we call as a causal mapping, which led to the development of causal loop diagrams to identify what are the key variables within the system. Let us map out their interaction, and then let us use that to move into stock flow diagram, where once we start doing stock and flows, we are already one step towards building a computer based model, which you will see why in a minute, because they are just visual representation of the underlying equations that you are trying to model and establish. Okay. So, and it is quite easy to teach. Use, that takes time. Yeah. So still, so MIT, then the Swayam School of Management has a pretty strong group on this system dynamics group. Still, the most of the activities are concentrated there. A fair bit of participation now from various industries and countries, and applications from the government all the way to people wanting to just learn and understand the systems on an individual level. Various nice things that has happened over time. People have then used the model to help predict. There's a very classical book by Meadows on limits to growth, which actually points out how that was a time. Remember, in 60s things was all great. It was fantastic. There is no, in fact, there is no limits to growth at that point in time. When a book on based on system dynamics ideologies, methodologies came about talking about that there is going to be limits to growth, and then that started unfolding in the 70s and 80s. 1980s system dynamics methodology was used in a Supreme Court or maybe a district court. I don't know, some legal hearings between a customer and the government, saying that meaning the client was telling that the delays in the project was due to the interference by the government because of changing requirements. Government was trying to sue the company, saying that you delayed the project unnecessarily, so I'm not going to pay you the full money. But the system dynamics model was used to understand actual dynamics between the government as well as the company, and it was found that there was excessive interference in the government which caused the delays, and the ruling was had used this system dynamics methodology. So that was quite, how often you hear that actual math is used in court case rulings. So it was quite interesting. And more recently, the I don't know how much of you are following the debates and discussions on climate change. There is this conference of parties, and one climate change model has been adopted by all the countries. So, so this model has been developed based on system dynamics methodology. The underlying model or the system dynamics model, which has been adopted as one of the most accurate models to represent what can happen in climate change and what are the potential pathways that it predicts based on our current consumption and usage patterns of various fuels, etc., and economies and stuff like that. So it's called C roads, climate road map something. So to look it up. So there are a lot of interesting and very high level applications that is coming out of this methodology.